Hello everyone. Thanks to everyone for watching this video. My name is Qi Dang. I am an architect and engineer. Today's video is titled Linear Programming, and it is going to introduce the simplex method to solve linear programming problem. I am going to give you an overview of what I am covering in today's video. First at all, it is a bit of background to the topic, and then focus on the simplex method before wrapping up with conclusions. Now I will provide an introduction for linear programming. We will look at the problem. Probably, we have all thought about a simplified diet problem. So the setting of the problem is the following. We need to eat food every day, and the food has nutrients for us to survive and stay healthy. We need to have somewhat balanced nutrients. The goal is that we want to minimize the cost of the food. At the same time, the daily requirement of the nutrients must be met. In the setting of this simplified problem, we only choose two different types of food. We know there is a broad spectrum of nutrients that humans need to simplify the discussion. Let's focus on three types of nutrients, namely protein, vitamin C, and iron. It is always useful to list your information in a tabular form. In the last column, it is listed the price for each of these foods. The price is set per unit. In order to live in a healthy way, you need to have some minimum intake of all the three types of nutrients. This information is listed in the last row, which we called minimum. Since we have only two different foods, we need two variables that we call them x1 and x2. For the cost function, it is a function of x1 and x2, and we'll have two terms. That is the 10x1 plus 4x2. We now collect the constraints. The total number of constraints remain the same, because we have to make sure the minimum of these three groups of nutrients must be satisfied. And what is simplified is the left-hand side of this inequality now contained only two terms. We have four constraints. We see that now we have a problem to minimize the objective function. The function depends on two variables, and we have these four constraints. Now we will introduce a graphic solution method to solve this problem. Since we have only two variables, x1 and x2, now we can visualize the constraints in the plane, a two-dimensional plane with coordinate x1 and x2. We consider all the constraints, and then we obtain a shaded region in gray, which is the feasible region. Now we consider the cost function. I'm given the constant called capital K. I want to find out the region or the line or the curve in the x1, x2 plane, such that the cost function equal to this constant K. That means I'm dealing with this equation here. Since this left-hand side is a linear expression, we know that it is a straight line. The slope of the line is negative 2.5. For different k value, we will have parallel lines. They all have slope negative 2.5, but they are parallel to each other. Let's take a look at the graph. Here is the graph of something we call the level sets or contour lines for this function. They are all straight lines with the same slope. We see that if we hold the dashed line and move it in a parallel way upwards, then the x1 and the x2 will be increasing, and therefore the k value is increasing. If I move the k increase, then the cost will be larger. If I move the k lower, then the cost gets smaller. Now it is time to put the cost function level sets over the feasible region, which is the gray area. The goal is that we hold the line with a fixed slope, and then we move the line lower, and the cost gets smaller, until we just touch the feasible region. Here you can see it will become this red dot at the vertex. At that point, the cost function will have a minimum value. To conclude it, we know that at this corner point with the coordinate x1 equal to 6, x2 is 21. To find the minimum value all we need to do is to put the coordinate into the cost function and obtain 144 cents. However, if we want to eat more food, then we will have more than 2 variables, so we cannot use the graphical solution method to solve the new problem. Next, we will introduce the simplex method to solve linear programming problem. In the simplex method, we will have a standard form for all the linear programming problems. We will rewrite everything into this form, but before we do that, let's give a formal definition of what we mean by a standard form, which is the following. We want to minimize a function which now we denoted as z, and we have n variables x1, x2, all the way to xn. Z is kind of a linear combination of all these variables with the coefficients. We call them c1, c2, and cn respectively. There could be a constant term here, z0. That is the function we want to minimize. We always require the variables to be non-negative, because they are physical quantities. All the xj for j from 1 to n, they are all bigger than or equal to 0. So here is the standard form. In here, the variables are x1, x2, all the way to xn. This z here, which is the value of the objective function. All the others, this aij, the cj, there are the coefficients in the objective function, and bi, these are the right-hand side of the constraints. z0, which is the number here in the objective function. All of these are given constants. They are set at the beginning of the problem. Take a closer look at this standard form. And one thing to catch attention is the constraints. We have seen in our example would carry inequalities as concerns as the condition bigger than equal or less than equal to. In the standard form, it is all stated with equal sign. Another thing, the number m here is the number of constraints. The number n of variables might not be the same number as the number m. Let's go back to a practical issue. We have claimed at various times that one can transform all these linear programming problems. We can transfer them all into the standard form which we have just defined. Let's take an example. We want to transform the following linear programming into standard form. For any less than equal sign, if you should have, then you add a new variable xk to the left, and then change it into equal. Then you require this variable to be non-negative. For an inequality with bigger than equal signs, such as constraint 2, then you add negative xk to the left and change it into equal sign. Then you require the variable to be non-negative. These new variables are called slack variables. In order to obtain the final solution, we can pivot these variables to make the standard form become canonical form. Now we will learn the canonical form. We want to minimize z with the following. So here the equations are the m constraints. The last one is the objective function. We know that for a linear programming problem to be in canonical form, it needs to satisfy 3 conditions. Number 1 is the constraint. The set of equations for the constraint shall be in canonical form, meaning you should have a set of basic variables here is x1, x2, and xm. They are written here in a diagonal form because all the other coefficients in the other equation. There is a set of non-basic variables from xm plus 1 to xn, and then has a right-hand side. That is the first part. The second part is the objective function. You see the objective function, which is z here, is expressed in terms of xm plus 1 to xn. So, a linear combination of the non-basic variables and z0, which is just a constant. The third part is the basic solution should be feasible, which basically requires all the b's here on the right-hand side to be non-negative. Let's see, we have that m is the number of constraints, n is the number of variables. We assume n is strictly bigger than m. For the canonical form, we just relabel the variables such that the first m of them are basic variables, and then the remaining is a non-basic. The basic solution and the feasible solution would be the xi is just a bi for I from 1 to m, and then the other xi's for the non-basic variables. They just take value 0. Basic solution z would take the value negative z0, because the left-hand side is 0. Next, we will go through a big summary for the complex method, starting from the canonical form. Step 1. You will check the coefficients Cj. If all of them are bigger than 0, then you know the minimum has been reached. Then you stop. Step 2. Then we check if there exists and k such that ck is less than 0. In that column, you look at the coefficients sik's. If they are all less than or equal to 0, then the minimum value of z is unbounded below. It is negative infinity, and follows from theorem you unbound it, and then you stop the algorithm. Step 3 is the main step. If there is a ck that is less than 0, and in the column, some coefficients are positive, you want to do a pivoting process. You would choose the column for pivoting k. Let's say column number k. This would be the column where the Cj is negative. If you shall have multiple terms of Cj that are negative, you will pick the one that is most negative, that is the largest absolute value. In order to pick the corresponding row, then you will look at that column, and then you compute the ratio of bi over aik for all the aiks that are positive. Find the minimum of this ratio, and pick that row as. Your pivoting point is column k, row s, and you perform the pivoting process. After the pivoting, you would have a linear programming problem, which is again in canonical form, and now it will have a different basic variable set with one variable changed, and they will have a different basic feasible solution. Now you go back to step 1 and repeat. The process might have to be repeated multiple times until you stop. Then you have found the minimum, or you conclude the minima is unbounded. Let's take an example. We want to maximize this function subject to 3 variables restricted. The constraints now are given as inequality. This means that this problem that is given here is not even in standard form. So we need to write it in standard form. And then in canonical form, the new standard form is shown in right-hand side. That is, use the select variables to put it in canonical form. Now let's use the simplex tableau. The first part of the tableau is exactly the previous canonical form. If I have the objective function here, I need to check if any of them are negative. And then I find that all of them are negative. So I need to choose one that is the most negative. I see these negative 3 are the same, so I just have to make a decision. It doesn't matter which one you pick. Let's say I pick the x2. Then I will look at this column and to pivot them. Then we obtain the next level of the tableau. In the second part, we see that this is one negative term in the objective function. This will be the column I will consider a pivoting point. After the pivoting, we obtain the third level of the tableau. Check for optimality. Let's see in the objective function, the coefficients here are 1, 1, 1, and nobody is negative. So I conclude that optimality is reached. The minimum value is negative 70. It is obtained at this basic solution. x1 is 8, x2 is 18, x6 is 70, and other 3, x3, x4, x5, they are 0. The final solution is shown in right-hand side. The observation and the remarks are shown in this slide. From conclusions, what we learned? Linear programming is a method to achieve the best outcome in a mathematical model whose requirements are represented by linear relationships. In mathematical optimization, simplex method is a popular and useful algorithm for linear programming. Okay, Thanks to everyone for watching my video today, and I do hope you found the video informative and that you learned some things from it. If you do have any questions, then you can write comments and messages. I am happy to answer any questions. Thanks for your watching.